All right, now we're completely ready to state the fundamental theorem of linear algebra, part 1. Part 2 will come after the test. And in fact, I'm hoping that most of you are able to get exactly where this is coming from. So the fundamental theorem of linear algebra part 1 talks about the dimensions of the four subspaces. So it just tells us what the dimensions are. The four subspaces. So just for a bit of visualization, let us write the matrix A. It's some matrix with m rows and n columns. And let's say that A, after elimination, has R pivots. Okay, so this is very important. The rank of the matrix is R. And R is, the rank of the matrix is obviously the number of pivots, which is not always visible directly in A, but it becomes visible once you carry out that elimination. So now with this, and we talked about how to find a basis for the column space, how to find a basis for the row space, we can state that the dimension of the column space of A is exactly the rank. Why is that the case? Because we talked about finding a basis for the column space that consists of the pivot columns. Well, if there are pivots, there are pivot columns. So I can say that the dimension of the column space of A is the rank of A. Now, the dimension of the row space, which is the column space of A transpose, is also R. Why is that the case? Because if you were to transpose the matrix and carry out elimination, you would still have R pivots. Those R pivots will be in the rows of A, which have pivots. So the pivot rows would give us a basis for the row space of A, and therefore the dimension of the row space is also R. So this is very interesting. The column space of A is a subspace in Rm, whereas the row space is a subspace of Rn. So Rm and Rn, these are usually different spaces. You could have R3 and R7. But the subspaces defined by the column space and row space respectively have the same dimension, which, as I noted yesterday, is a measurement for the size of a space, right? If they're both planes, they could be planes in different subspaces, but they would sort of have the same size. Now, the dimension of the null space. What is this? Well, remember that the way we find the null space is we look for special solutions, which are, and we get one special solution for each free variable. So if there are R pivot columns, then we would have the remaining columns to be free columns. So how many free columns are there? So again, there are n columns in total, and there are R pivot columns. So the remaining n minus R columns must be free. Therefore, the dimension of the null space is n minus R. By symmetry, we know that whatever is true for the columns of A, if we just flip it for the rows, that's how we get the null space of A transpose, or the left null space. So the dimension of the left null space of A is m minus R, which is all the rows minus the pivot rows. It gives us the free rows. So something that we've already used, we're just now making formal. Now, I'll be honest and I'll tell you that If you asked me to state the fundamental theorem of linear algebra with an m and an n, I would really have to stop and think, was this m or was it n? And the reason is that our brains don't really work very well when we have these imaginary examples. But when you have a specific matrix, for example, let me write, and I'll write a reduced one just so that we can see everything. So let's say we have a matrix A that looks like this: 1, 0, 0, 0, 0, and then maybe 0, 1, 2, 3, 4, and then let's say a row of zeros, for example. So what do we have here? Well, we have two pivots, obviously. We have one row which is linearly dependent on the other two. A row of zeros is always dependent on the other two rows. You can always say it like that. Or rather, a combination of rows or a combination of vectors that contains the zero vector is always going to be dependent, because the way you could combine the three rows in a non-trivial way could be take 0 times the first row, 0 times the second row, and 1 times the third row, and you will get a 0. So that 1 here says that the combination would be non-trivial. Anyway, for the purposes of dimension, we see that there is only one row with 5 components that is linearly, that is free, let's say free. So I know immediately that the dimension of the null space for this particular example would be 1. I don't even have to care about what is the meaning of m and what is the meaning of n, right? The rank is 2, so I know that the column space will be 2-dimensional, the row space will be 2-dimensional. Now, what about the null space? Well, I'm counting those columns that do not have pivots. Clearly, there is 3 of them. And for the left null space, as I said, I count those rows that don't have a pivot. Clearly, there is 1 of them. And I didn't have to use the fact that this matrix was 3 by 5. So what I'm trying to say here is, don't try to memorize this theorem, but rather to understand where it comes from. If you remember that the column space and row space are defined, or the basis for them is defined by the column rows or the column pivots, the pivot columns and the pivot rows. Sorry, I misspoke. Then all the other rows. So this is not to say, you see, these 3 columns, all this says is that they depend on the pivot columns. And with that, I know that the null space of A will have a dimension 3. That's not to say that these 3 columns give you the null space. Be very careful with that. We'll solve examples just to remind ourselves, because the null space says that it consists of combinations. So I need a vector that combines all 5 columns of A to give me 0. So the null space, because it combines 5 columns, it's a subspace of R5, just like the row space. Whereas the left null space combines 3 rows, therefore it is a subspace of R3. So maybe I should write that. Just to make sure we all understand what we're doing. So the column space of A, you see each column, actually I'm not trying to make it equal to anything, I just want to say where it is. So it is a subspace. That's what that symbol means, a subset or subspace for the time being, of R3. Why? Because the columns of A are vectors with 3 components. The column space of A transpose, which is the row space of A, consists of vectors with 5 components. So this is a subspace in R5. The null space of A, well, the null space needs to tell me how to combine all the 5 columns of A. Therefore, it must be a subspace of R5. And the left null space of A, it tells me how to combine the rows of A, but A has 3 rows, therefore this is a subspace of R3. So I don't have to memorize these things if I understand what each subspace is actually consisting of. If I understand what the subspaces are, then I will figure out how to determine all these numbers. All right, next video with a complete example for a matrix, matrix A, we will reduce it all the way, determine a basis for all of these subspaces, and redo the exercise of finding the dimensions.